Hello everyone, I am Armin Vakil from Penn State University, and in this video I'm going to present our paper in Sigmatrix 2020 titled DSM, a case for hardware-assisted merging of DRAM rows with the same content. If we look at today cloud servers architecture, they consist of multiple computing elements such as CPUs, GPUs, FPGAs, and even TPUs. And all these different computing elements operate on memory. As a result, the demand for DRAM memory has increased to keep up with the high need of these computing elements. However, if we look at DRAM memory capacity scaling, it do not scale with the same pace as these computing elements are scaling, and this DRAM scaling introduces both power and performance issues that are now more important than any time. To elaborate more on the importance of this problem, let's look at how DRAM contributes to the total power usage in data centers. This figure shows that DRAM memory accounts for roughly 20% of the consumed power in data centers, and one of the main contributing factors in this high energy consumption is memory refresh. In our evaluation, we showed that this memory refresh energy consumption accounts for about 7 to 50% of the consumed energy in 4 GB to 64 GB DRAM memory devices. So an important question is how we can reduce this overhead in data centers. To answer this question, let's look at the environments that we are targeting and kind of applications that execute on these systems. Cloud servers usually host multiple virtual machines to service multiple users at the same time. And these virtual machines typically use similar or even identical kernels and libraries. In this work, we are going to answer the question of how can we leverage this opportunity to reduce the memory refresh overhead. In this work, we have the following contributions. We first propose DSM, a lightweight hardware extension that detects different rows in DRAM that have the same content and refresh only one of them. And with this, DSM can skip 47% of memory refresh commands and reduce the memory energy consumption by 8.5%. Also, with reducing the time in which DRAM is refreshing memory and not servicing the memory requests, DSM improves the 99th percentile latency by up to 8.2%. In the rest of this talk, I first go over some background details on DRAM and cloud systems, and then I provide some motivational results that shows the opportunity that DSM can leverage. Then I will talk about the design of DSM and some evaluation results. And finally, I will conclude my talk. DRAM chips are composed of multiple ranks, and each of these ranks has multiple banks. Then inside of each of these banks, we have multiple rows, and each bit in memory is stored with one transistor and the capacitor that is shown by a circle in this figure. These capacitors are volatile and they lose their data or charge over time. They need to be refreshed every 64 milliseconds. DRAM vendors, for increasing the size of memory in their newer technologies, first reduce the size of each cell. That means each capacitor can store lower amount of charge and lose its data or charge faster. This will result into that memory cells should be refreshed more frequently. Second, for increasing the size of memory, DRAM vendors increase the number of rows in each bank. That means during refreshing a bank, higher number of rows should be refreshed. That again results into longer refresh time and unavailability. Both these have adverse effects on energy consumption and performance of the system. Now let's first look at the energy overheads of memory refresh. If we follow the trend of memory refresh energy consumption for different DRAM device capacities, the wasted energy that should be consumed only because of DRAM refresh that don't result to any computation increases by the size of memory, but it can be up to 54% in 64 GB DRAM memory devices. We secondly look at the implication of memory refresh on the performance. Memory refresh can result into hiccups in memory access latency, as certain sections of DRAM, whether one bank or all banks, based on the refreshing policy, are not accessible during refresh. In this experiment, we show that removing all memory refresh overhead can improve the 99th percentile memory access latency by 6 to 9x. By closely looking at the cloud system's hardware-software stack, we have the hardware on the bottom, and then a hypervisor or host operating system that is responsible for both managing and sharing this hardware between multiple virtual machines. And each of these virtual machines have their own operating system that has different libraries, and on top of these libraries, the applications are running. Then hypervisors consolidate multiple virtual machine instances on top of this hardware to increase the utilization. These different virtual machines usually use same or even identical operating systems, such as different kernels of Linux. Moreover, all of them uses identical libraries, such as C++ or Python libraries. And finally, these applications may use similar frameworks, such as TensorFlow. This type of consolidation results into having same value rows in memory. To illustrate more on the amount of these same value rows in the virtualized system, we ran 4 virtual machines on a real system with 16 GB memory and let KSM, that is a kernel module for merging same pages in operating system, to merge as many pages as it can for 5 minutes. And as it is shown in all these figures, even before running the applications, there are 300K pages that have the same value. And this number will increase by another 100K pages during the runtime of applications in some cases. Now let's look at how we can leverage this opportunity to reduce the memory refresh overhead and what are the challenges to do this. Assume we have 4 rows in memory, that 3 of them have the same value A. Since these rows have the same value, the goal is to merge these rows into one representative row and only refresh this row and skip refreshing other ones. Now the question is how we should keep the integrity of data, and we should, upon a read request, the memory should return the correct data to the computing element. And also for write requests to a row, this write request should only change the return row and not affect other rows that are merged with this row prior to write. To exploit the same content opportunity for reducing the overhead of memory refresh, we propose DSM. And these main design goals for designing DSM are: first, tracking rows with the same content and refresh only one of them. Second, keeping the mapping information of all DRAM rows and redirect the memory accesses if the accessing rows are mapped to another row. One of the main informations that we need to keep track of is the mapping status of each row in memory. For each row, we should know whether is it mapped to a representative row or not, and if yes, which representative row it is mapped to. And in addition to this, we store another information that whether a row is 0 or not. And if it is 0, we can just send the data to the computing elements without even accessing DRAM. However, simply mapping any row to any representative row can have high overheads. Let's look at this example again, that we had 3 rows that have the same value and 2 of them are mapped to the representative row and do not refresh. Now upon a write request to this representative row, we should know which rows are mapped to this and copy the value of to them so the rows that are not refreshed don't lose their data. To collect this information, we need the reverse of mapping table that has high overhead for both keeping and maintaining. Instead of doing this, we reserve 2K rows or 3% of rows in each bank in memory that are not accessible by OS, and DSM uses them as representative rows, and we call them R rows. Since these rows are not accessible by OS, there will not be any writes to these rows, and DSM do not require to maintain and keep the reverse of mapping table. Consequently, each mapping table entry only requires the index of the R row that the corresponding row is mapped to in case of a merge. And we put this mapping table inside memory and cache it inside memory controller. This table also stores whether a row is 0 or not. In addition to these tables, we have another data structure, counter checksum values. That in this table, we store the checksum value of each R row, as R rows are the best candidates for merging, and DSM uses this checksum for checking the potential of same value in different rows. DSM also has a counter for each R row that shows the number of rows that are mapped to this R row. This counter is necessary for the replacement of R rows, and we cache both counter and checksum value of R rows inside memory controller. Please also note that these data structures are not shown to scale, and they are only roughly 3% of each bank and memory. For more details on this, please look at our paper. Now let's look how DSM works in action. Upon a read request to memory, we put this request in read queue and look up mapping table cache in parallel. If row X is mapped to another row like X prime, then we simply change the address in the read queue and redirect the memory request to the correct row. On the other hand, if X is not merged, no further action is required and we don't need to change the read queue. Upon a write request to memory, we again simultaneously put the request in write queue and look up mapping table cache. If the row is not mapped to any R row, there will not be any change, and the write request can proceed as normal. On the other hand, if the row is mapped to another row, the row X is mapped to another row like X prime, we should copy the content of X prime to X, and then issue the write request to X. For efficiently doing this copy operation, we use a row clone that simply copy one row to another row inside DRAM. For calculating whether different rows in memory have the same value with R rows or not, DSM should periodically look up different rows in memory and compare them with R rows. To be more specific, DSM fetches one row from memory and computes its checksum and compare this calculated checksum with the checksum of R rows that are cached in R rows counter checksum cache. Then in case of a match, it will fetch both rows and check if their content really match or not. And if they really have the same value, it will update the mapping table cache and the counter of the corresponding R row. Now for refreshing banks in memory, as the refresh schedule of each bank is predictable, DSM can populate the refresh bitmap over time before the refresh interval of each bank by reading the mapping from either mapping table cache or mapping table in case of a miss. And then during refresh, DSM perform the refresh operations based on this calculated refresh bitmap. And please look at our paper for more details on this. To evaluate DSM, we use Gen 5 simulator, that is a cycle-accurate architectural simulator, and we ran 4 VMs inside Gen 5, and on each of these virtual machines, we run a mix of benchmarks from Tailwind Suite and memory-intensive applications of SPEC 2006. Then to see the effectiveness of DSM, we compared it with 2 other configurations. First, baseline, that is refreshing all rows of each bank. In addition, we compared DSM with no refresh configuration that assumes DRAM cells do not need refresh, and this is our ideal case. For more details on the evaluation methodology of DSM, please look at our paper. In this first experiment, we evaluated the IPC improvement of DSM that shows by reducing the time in which a bank is not accessible because of memory refreshes, DSM can achieve up to 4.2% IPC improvement, and it can also improve IPC by 2.4% on average. We also estimated the impact of DSM on tail latency, as it plays an important role in cloud servers' total cost of ownership. And DSM can improve the 99th percentile latency of tail latency sensitive applications by up to 8.2% and 4.4% on average. Finally, we evaluated the effectiveness of DSM on optimizing the energy consumption of memory. DSM reduces the memory energy consumption by up to 8.5% and 6.7% on average, which simply is keeping the unnecessary refresh commands in DRAM. To conclude my talk, in this paper we addressed the scaling problem of DRAM memory and reduced the performance and energy overheads of DRAM refresh. We proposed DSM, a hardware extension to detect rows with the same content in memory and refresh only one of them. We reduced the energy consumption of memory by up to 8.5% and also improved the 99th percentile latency of tail latency sensitive applications by up to 8.2%. Thanks for joining my talk.